Welcome back to Renewable Energy Technology course, and this is lecture series 1.2 part 2, and we are discussing about micro small hydro components design guidelines. And in the earlier part 1 we have discussed about the different civil components, and now I am going to discuss about the electromechanical components, basically hydro turbines, generator and electronic load controller and other governors. Hydro turbines. Basically, hydro turbines are the machines that converts the kinetic energy into the mechanical energy, and the classification of hydropower can be based on the flow path. It can be axial flow, radial flow, mixed flow. If the fluid is working in a direction axial to the shaft, then we say as an axial flow turbine, and if the turbine in which the flow working is in the radial to the shaft, then we say radial flow, and if the flow is mixed type, then we will say it's a mixed flow. And Francis turbine are the mixed flow turbines, whereas Kaplan turbines are the example of axial flow turbine. Turbines can also be classified based on the pressure change. They can be classified as impulse turbine and reaction turbine. And the impulse turbine are the turbines that change the direction of flow of a high velocity fluid. The resulting impulse spin the turbine and convert it into the mechanical energy, and after the change in the direction of the flow, the fluid will drop back with the diminished kinetic energy. While in the reaction turbine, the turbines develop torque by reacting with the fluid pressure and the mass, and the runner blades themselves arranged to form convergent nozzles. You can see those changes in this diagram, the pressure and velocity relations. I would like to give an examples of impulse turbine. Pelton turbine is one of the examples of the impulse turbine, and the Pelton turbines are the turbines that are normally used for the high heat projects. And this, in the Pelton turbines, you have runner buckets. You can see in the drawing here, diagram, this is the stainless steel runner bucket, and you have nozzles, and these nozzles can be one nozzles, multiple nozzles, depending on the flow and the designed head. And you can see here the turbines systematic diagram here, where you can see the buckets and you can see the nozzles, and also there is a spur rod to control the nozzle valve. And there is also a deflector plate, and this deflector plate is mainly used for the emergency purpose. If there is a sudden change in the voltage or a speed in the generator, then the function of deflector is to actuate it to control the flow, so that the flow will not strike on the bucket, and it just strike on the deflector, and the water will drop down to the tail race without moving the turbine. So the main purpose is to save the turbine going over speed during the time of emergency. And another example of impulse turbine is cross flow turbine. A cross flow turbine is a drum shaped and used as elongated rectangular section nozzle, and this is directed against the curved vanes on a cylindrically shaped runner. And this kind of turbine is mainly used in micro hydro ranges, and cross flow turbine is not meant for big hydropower projects. And the reaction turbines, Francis and Kaplan's turbines are the examples of reaction turbines. Here is the example of Francis turbine. Francis turbine is most widely used turbine, and this is as I said earlier, this operates in the medium heads and also medium range flow. Francis turbines are radially and mixed flow turbines and fully submerged. They consist of guide vanes, runner parts, and the draft tube. And for the Francis turbine, the net head is difference between the upstream and the tailless level. So, it utilizes the draft tube level as well. And the modern Francis turbines can have the efficiency up to 95%. So, it is one of the efficient turbine. Here is another pictures of how the Francis turbines runners look like. Kaplan turbine is another axial flow turbines with a variable pitch blades, and the hubs contains a mechanism called combinator, and this enables the blade to tilt to be changed automatically with respect to opening of the guide vanes. Thus, the fluid meets the blade tangentially. With the rotating blade, it can achieve the high efficiency as 90 to 93%. You can hear more about these turbines in the session when you are discussing about large hydropower with Mr. Babak. Now, how to select turbine? So, normally in general, if you have a low flow and if you have high head, you choose Pelton turbine, and if you have medium head and medium flow, then you will choose Francis turbine, and if you have high flow and low head, you will go with the Kaplan turbine. And also you have cross flow turbines for the medium head and for the medium flow actually, or low flow, but for the small scale range, and that's the cross flow turbine is used in the micro hydro for that range. But specifically when you want to design a turbine and select a turbine, then there is a specific terminology called specific speed, and that determines which turbine to select. And the specific speed of a turbine is the speed at which a similar mode of turbine, when it runs at a 1 meter head, and when such size develop 1 kilowatt, that speed is called specific speed. And the type of turbine is determined by the specific speed, and specific speed can be calculated as with the following equation, where Ns is a specific speed, and this is given by 3.65 times the turbine speed into the discharge to the power 0.5 divided by head to the power 0.75. And once you calculate this specific speed, and then you can choose among the different turbine options depending upon the range. So, if you look at here, the Kaplan turbine has a specific speed range from 270 to 1000, Francis turbine has a range from 60 to 350, and Pelton turbine have a range from 8 to 72, and cross flow has a range from 42 to 170. There are also charts available to calculate, to select the turbine size or the types of turbine. Here you can see the turbine selection chart, and now look at this curve. So, in the x axis you have the flow in meter cube per second, and in the y axis you have net head, and based on the head and the flow, and there are different range of turbines available. And also you can see that in some range you can have two different type of turbines. For example, let's take a place where you have a flow of 1 meter cube per second and a head of 50 meter cube per second. And in that case, you can use either many turbines can be used here, and mostly suitable is the cross flow turbine and the Pelton turbine in this range. And the important things to understand here is not only this curve will determine the selection of turbine, but if two types of turbine can be feasible in this particular range, then you have to also look at the different other characteristics of the turbine that might influence the selection of the turbine, and one of them is the part flow efficiency. Here you can see the different turbines, and the different turbines have different efficiencies in the part flow. So, if you look at this one, the fixed propeller turbine has a very poor efficiency, part load efficiency, and the the good turbines with in terms of part load is the full Kaplan, and also the Pelton turbine has better efficiencies, and also the cross flow efficiency is not so good. You can see here with this line. So in that sense, even if the cross flow and the Pelton turbine are feasible in that particular head and flow, we'll prefer to choose Pelton turbine because of higher part load efficiency. After finishing the discussion on the turbine and turbine selection, I would like to start a discussion on generator types that are used in micro and small hydropower plants. So there are two types of generators that are used in micro and small hydro. They are synchronous generator or asynchronous, which is also not an induction generator. And normally, if you are building a small up to 15 kilowatts power plant, then we normally choose induction generator, which is also cost effective in a way. And if you have the load mostly resistive, in that case also we go with the inductive one. But as you go in the bigger size of the power plant, then normally synchronous generators are selected. However, I am talking about this in the context of isolated power plant. But if you want to connect the power plant in the grid with a bigger, little bit larger size of the plant, let's say 1 megawatt or 5 megawatt plant, but in that case you can use even the induction generator, and the induction generator are manufactured in that range, and you can get directly induction generator. Whereas in the small range, the induction generator itself might not be available, but you have to make the induction motor to run as an induction generator. Now I'll start with the synchronous generator. In the synchronous generator, the waveform generated voltage is synchronized with the rotor speed. So in that case, the frequency is given by Np divided by 120, and where N is the rotor speed and P is the number of poles. And in this type of generator, you have to give the excitation system. So you can have a separate DC excitation system, or you can also have a self-excited synchronous generator. But even in that self-excited synchronous generator, one thing you have to remember is if you are starting the generator after a long time, then sometimes you may have to have some DC power backup, so that you might need to give some initial excitation, because if the plant has not been operated for a long time, or it is operating for a first time. Otherwise, we can also have self-excited generator systems in the synchronous. And another one is the asynchronous generator, and this operates mechanically, turning the rotors faster than the synchronous speed. And once you try to use, or you try to run the motor faster than the synchronous speed, then it will start acting as a generator. And normally, when you connect this to the power system, it will always give the active power and try to take the reactive power for the excitation, field excitations, if you connect it to the grid. And if they are in isolated mode, then maybe they need capacitor bank to operate in the standalone mode. Now, sizing the generator size. Once you know how much power you are going to get from the hydropower, and if you know if you are installing a power plant of 50 kilowatts, then how do you select the generator kVA size? So normally, if you are selecting a power plant for a micro range, then in that cases, when you have to choose from the available sizes in the market, then you also need to understand that these generators are affected by the working ambient temperatures, the altitude factor, in which altitude you are going to operate that, especially when it's in the hilly and mountainous regions. This can have a good impact, adverse impact, in a sense that you need to consider this altitude factor. And also, if you are using electronic load controller as a governor, then you should also use this factor in the sizing the generator. And also, what kind of load you are using. If you are using only the resistive load, then you can use the power factor as 1, and if you are using some other inductive loads, then the power factor we choose is 0.8, the factor. And with all these factors, you can determine the size of the generator, and also sometimes if you are using the generator in the isolated mode, then you also use a safety factor, and this safety factor is provided based upon how big size productivity end use motor you are going to use for that particular project. So in that case, because of this high starting current that is needed to run this large motors, it is recommended to put some safety factors in the generator's kVA sizing. Governing system. Governing system is basically an essential device which controls the speed or the power output of a turbine. And there are two kinds of governing systems that are used in the hydropower. One is the hydraulic governor, and another is electronic load governor. And the hydraulic governor has a role to assure the constant speed of generating system, and hydraulic governor does it regulating the turbine flow. Another type of governor, as I said, is the electronic load governor, also known as electronic load controller, and mostly these are used for the small power plants and in the off-grid settings. And this keeps the generator load always constant by distributing the load as a primary load to the consumer load, and also if the load is not utilized in the village or by the consumer, then the load is diverted to the dump loads, which is also known as secondary loads. And this is how it looks like in the system. So if the consumers are not using the design output power, then some of the load is diverted towards the ballast load by actuating this thyristor control system, and that is that you have this PL controller, and that controller will actuate this thyristor based ballast load. And if the load is high, I mean if people started using the load let's say in the evening time, then again some of the loads that have been diverted towards the ballast load is controlled, and system output is always maintained as a constant for the generator. So with this, I would like to end lecture series 1.2, and I hope you have understand the basic guidelines of how to design a micro hydro components. Thank you for listening.